The talk title is same. I mean, you can almost assume that it's a continuation, although I will try to recapitulate a little bit wherever we had ended on day before yesterday. So, okay, so what we have learned is other day is I am in synthesis of self-organized nano patterns. Okay, and regarding the definition of self-organization, what happens in case of iron-induced pattern formation is nothing other than the fact that the surface of the material on which we try to form the patterns, those get reorganized under ion radiation. So this is a real-time morphological image obtained from atomic force microscope machine, and so it's generally at an oblique incidence for low or intermediate energies, meaning a few hundreds of electron volt up to a couple of hundreds of kilo electron volts, so of ion energies. We can get these things, and advantages of ion beam induced pattern formation are several, but out of those we can have a look into it, that it's considered typically to be a single step processing route for large area pattern formation, and all the way up to wafer scale integration of 2-inch wafers that we have done in our laboratory itself. It's a faster and cheaper compared to conventional lithographic techniques. Then the pattern parameters are tunable. So this offers large variety of nanoscale pattern formation. So that's a possibility. That's a huge win-win situation. So it's not restricted for the electrical conductivity of the specimen, the film or substrate that we intend to create patterns on. Now, let me tell you today our major research areas using nanoscale pattern surfaces in our laboratory, which is rather known as Surface Nanostructuring and Growth Laboratory at Institute of Physics, Bhubaneswar. As you can see, once we fabricate these self-organized nanoscale patterns on wide variety of materials, we not only fabricate, we have but also tried to understand the underlying physics-related mechanisms which give rise to such pattern formation. At the same time, what do we do with these patterns? Let them be patterns, but what do we do with them? So here we can see very well that we can actually make use of these pattern surfaces in various physics or materials research related problems. For instance, among many, I mean, few have been jotted down here where we have been working since last 7-8 years or so. And now I realized actually while we are preparing this long talk that there are a lot of interesting data, and almost 95% of those data we are already published by us. Few are still going on. Nonetheless, my today's application related results will be covering or say be touching upon these related physics or materials science related areas. So please keep it in mind. I will slowly try to unfold those results. Now, well, I mean, as a recap, I mean, low energy ions particularly can give rise, are rather popular to give rise to self-organized pattern formation largely on semiconductor surfaces. Okay, and for instance, I have shown here several examples based on the elemental semiconductors and a few very important 3-5 semiconductors, although they're not limited, as I have told the other day as well. For instance, I have also shown the examples of oxide materials, pattern formation on oxide materials. And to name a couple of them is silicon dioxide and zinc oxide. This zinc oxide is our much newer result, although I mean it happens on TiO2 and L2O3, etc. Besides many of those other results that I shared with you on the other day. Now, this is just to give you a glimpse of what kind of fascinating patterns can be generated and why low energy ions are popular. Because if at all anything has to be talked in terms of optoelectronics industry, one has to have wafer scale integration. Wafer scale integration in terms of using conventional higher energetic ions, or rather ion producing equipment like ion implanters, and so they will be much more costlier compared to these low energy ion producing ion sources. Okay, because these are much tabletop kind of experiments, facilities where the ion sources cost probably orders and orders of magnitude less. I mean, maybe 7-8 orders of magnitude less, or at least 6 orders of magnitude less compared to the professional ion implanter facilities or say accelerators. So, with these few words, let me start going ahead. I mean, many important aspects of pattern formation are jotted down here in this book, which was edited by me and one of the past colleagues from Inter University Accelerator Center, New Delhi. He was the past director also there. Important thing is, please note down that although I have told you the other day that pattern formation using energetic ion beams actually depend on a large number of parameters, experimental parameters, for instance, ion energy and mass, ion flux, ion fluence, angle of incidence of the ions, substrate temperature, substrate rotation, presence of impurity, and so on and so forth. Out of that, almost every dependence I had shown on the other day. Now, this is just as part of recapitulation. As I told you, the story started altogether, this I did not show other day, way back in 1962, nearly 60 years ahead before, where this French group actually had reported that on glass sample, they could observe, okay, such beautiful patterns. And both, much talked about by me on the other day, perpendicular mode ripples and parallel mode ripples, where orientation of the ripple wave vector is either perpendicular or parallel to the beam, very clear from the arrow marks and the direction of the ripple patterns. Okay, so ion beam can generate periodic nanoscale patterns on material surface, and this is, of course, we have seen. And the beginning was basically to understand, mostly people started understanding till early 80s, early 90s or late 90s, that the common belief was that the surface was never a flat surface. I mean, ideally nothing is a flat surface. And so there was a tendency towards less sputtering near a trough and more sputtering near a valley. Obviously, there will be an instability. Okay, sputtered atoms will be more, okay, at the top, but there will be local roughness. Okay, and so this is from the famous review article on mechanism of surface micro roughening by ion bombardment with a real stalwart Danish professor Peter Sigmund. And this is a pretty old paper, nearly 50 years. The good part is Peter is still very active, although he has become very old now. But followed by this, I told you other day that this very work from the German group actually gave a huge boost to bring a lot of energy in this area. People started revisiting, because over this nearly 30 years of time, when those people, the French people, had first observed this pattern formation by iron beams, many people later on regularly used to see it, but they thought that it's a kind of problematic life to live with those kind of patterns, because people didn't want to see those patterns. I mean, they were unwanted. Not only they were getting surface roughness, but at the same time, the surface morphology was getting changed. So they were not only the fact that they were never thrilled, they wanted to avoid reporting those things. But then these people actually gave a new lease of life to this area when they reported, instead of the glass surface on gallium antimonide, and they could show successfully that with varying ion energy, the dot size actually kept on increasing, which was known as dot coarsening. Like the ripple wavelength actually increases or gets coarsened, okay, with increasing ion strengths and ion energy that we have seen other day, as it actually grows almost linearly, okay. And here the interesting thing is the dots were absolutely crystalline, okay. Nobody can in principle claim that a very little amount of amorphosity doesn't creep up, doesn't appear at some or other way in and around the the surfaces, okay. But nonetheless, the dots are mostly crystalline, as was observed from the high resolution TEM imaging. Now, once again, over the period of from 1962 to this Peter Sigmund's theory of 1973 on ion sputtering, this famous paper, rather theory by two gentlemen from the United States, namely Richard McBradley and Dr. Harper, came in between, and that was in 1988. This paper is now been cited for more than 1,000 times. And when nothing else was available, that means after this 1999 paper by the German group, which was published in Science, this one, after that for several years, whatever data people could obtain, they used to almost as a thumb rule used to say, so our data are nicely explained by Bradley-Harper theory. Now, what is this Bradley-Harper theory? I had talked to you a little bit the other day, today also even smaller amount. The prerequisite as per this linear continuum theory based Bradley-Harper theory equation, it's a continuum equation. And the prerequisite is that the surface, or rather the target, has to be amorphous. And this is curvature dependent, surface curvature dependent sputtering mostly. As I told you, I mean, it's very clear that there is again energy reaching to a point P, okay, due to an ion incident at a point P prime, okay. For a convex surface, you see, it's still within the energy ellipsoid. But for a concave surface, we can easily see that this point is P is out of the energy ellipsoid. That means the energy deposited along with the path of the in and around the path of the ion beam. So it's very clear that valleys are going to be eroded faster. So that's why this is the valley. So valleys here, more ion energy is getting deposited, and that's the reason physically it will give rise to erosion of physical erosion of many other atoms from the surface compared to the trough, okay. That is near the peak or whatever, if we assume that is some sinusoidal kind of surface near the peak. So this energy deposition is much less. So that's what valleys are eroded faster compared to the hills. And this leads to growth of surface perturbation or surface instability. So here, clearly, as I told on the other day, it's a competition between the sputter erosion. It's not only sputter erosion, because ion-induced diffusion will also be, surface diffusion will always be there. So apart from that, so it's a competition between surface, sputter erosion and surface diffusion, which gives rise to the surface instability and in turn formation of the ripple. Now, according to this theory, major success in terms of explaining is ripple formation. That is reasonably well understood, and ripple orientation switching at higher theta values. And the main drawback was this theory unfortunately predicted ripple, or still predicts rather, ripple formation at any value of ion incident angle theta as is been defined here. But we saw the other day, on many occasions, up to a certain critical angle, the surface actually doesn't show up any pattern formation, and rather remains as flat as the pristine surface to start with. So that means not even the surface roughening took place because of this competitive process. So the most decisive factor is given certain ion incident angle. If for that particular angle of incidence of the ion on the surface, if the ion-induced diffusion process becomes dominant, then the surface will remain flat, in the sense that will not swap with any kind of pattern formation. On the other hand, or rather in contrast, if it happens that this sputter erosion mechanism is more dominant, nobody can avoid seeing those, patterns to get formed. But what happened is, this is a fact of life. This is a statement of fact. We have seen large number of data in my previous talk. But what happens is, as a drawback, why is it called as drawback? That because this theory predicts that ripple formation will take place at any given value of theta. That means for all incident angular incidents, there would be ripple formation, which is not quite correct experimentally. So that's why it's considered to be drawback. Very important thing, as I had told you this equation also. This is the linear differential equation in the linear region, of course. Okay, where we get to see the ripple formation, and importantly, these Sx and Sy are the x and y components of the sputter erosion. So these are known as sputter coefficient. Okay, and these Sx and Sy terms, okay, these two give sputtering induced surface roughening, while this term actually gives the surface diffusion. Okay, please excuse me for a few seconds. So, and other important thing is I was telling again and again that the parallel mode ripples and perpendicular mode ripples, where in one case the direction of the ripple wave vector is parallel, and in one case is perpendicular to this thing, incident angular direction. Now, when the quantitatively from these equations, it is found that in case both the sputtered coefficient along the x and y direction, okay, are negative, then it has to be parallel mode ripples. Okay, and in case if Sy is less than Sx, but along the y direction, that is the sputter coefficient along the y direction is negative, then this ripple orientation rotation takes place, which is well explicable by this model. Okay, of course, this happens in between a certain critical angular window. That means this thing also has to take place, although the thumb rule is it takes place at relatively higher angles of incidence. And these happen at much lower, starting from much lower angles of incidence up to a certain angle of incidence beyond which this thing happens. Ripple orientation changes. Okay. And so we go next. And I told you that the other day that another competitive model came later, which was known as Cutter-Vizhnyakov theory. Okay, followed by actually little later. You can see the timeline nearly a decade later, Cutter and Vizhnyakov had first reported this Cutter-Vizhnyakov theory. So here, apart from sputtering and all, these authors also considered ion-induced mass redistribution. Okay, so according to these model also, there is a theory, there are certain successes, that is it also predicts ripple formation, but then from a critical angle theta c, so for instance. That's the kind of the theta c we talk about. Okay, and that's what we identified as the drawback of the Harper theory, where it predicts ripple formation at any value of theta. But here, for the Cutter-Vizhnyakov theory, that limitation is a little bit lifted. The restriction is a little bit lifted, or that drawback is a little bit lifted or removed, because this predicts ripple formation from a critical angle, certain critical angle theta c, that means certain angle of incidence for the energetic ion. Okay. And a very, very important matter here is its drawback. Drawback is very clearly, you see, for both sputter coefficients along x and y directions, we can clearly see, we have this 2 theta term involved here, particularly for the x direction directly. So this 2 theta term will give rise to a situation which will lead to a prediction of ripple formation up to theta is equal to 90 degrees. So you can imagine, this is the incident beam direction, this is the angle of incidence of the ions. Just think of what does it mean if the angle of incidence become parallel to the surface. Nothing. No experimental setup, no sample manipulator is available which can lead to let the beam fall on the surface at an angle of incidence of 90 degrees. That means the beam has to be falling parallelly. How much will fall? It will go just parallel, just run away parallel to the surface. Will not make much of a meaning at all, unless and until the surface is extraordinarily rough, and those hillocks will probably be bombarded and rest will not. So that's an impractical and improbable situation. Nobody considers that, and is rather considered as a drawback. Okay. Because nobody can do experiments up reaching that an angle of 90 degrees, and it doesn't make sense practically. Now, low energy ion radiation, we have already seen that a more visible way how one can visualize rather. As the energetic ions fall on a target, you can see physically ions will be getting eroded, or sputtering will take place, and at the same time you see the ions will go inside, and atomic redistribution will also take place, and due to diffusion. And what happens is basically surface diffusion will try to level the situation as well. So mass redistribution, okay, as per Cutter-Vizhnyakov theory will be present, and sputtering will also be present. And this will be actually depending on which one is winning the race, will decide actually that whether it will be the instable surface or not. That means pattern will be seen or not, as I told earlier. Okay, and once again, values will be eroded faster, as is more nicely I've tried to show here. So the sputtering yield or erosion from the valley regions will be much more than the hillocks of these shown here. Okay, And so mostly smoothing will be more prominent below key angle of incidence of 45 degree, and instability will prevail mostly more than 45 degrees. That's a thumb rule. Nothing is absolutely universally applicable, although we all in the community, in this community, are looking for such a unified theory which can very nicely predict that for which material, which is the angular window over which I can expect to see patterns, but through this ion-induced instability created at the surface, and where we should not expect to see patterns, rather we should see a flat surface as flat as whatever we had started. Okay, so this gives you fairly good visual idea to visualize things. And remember, this is the situation which prevails from room temperature up to 200 degrees centigrade or so, more or less, for silicon. Okay, and roughly for germanium as well. Now I'll come to those situations slowly. So amorphization of the crystal surface, actually for any semiconductor at room temperature or this kind of lower temperature, it takes place above the value of an ion fluence of 10 to the power 15 ions per square centimeter. So kind of ion fluence, those are needed, I mean that is needed to create instability or say give rise to pattern formation on any surface, let it be a semiconductor or an oxide or a metal, whatever. It always needs very high ion fluence, much higher than this, although small scale relief structure for mount formation is possible in and around this ion fluence for some select materials. One has to gain that experience. There is no thumb rule to do so. But yes, for which, I mean, what I want to mean is for which fluids, which material will swap pattern formation at a particular angle of incidence is not known. However, I will come slowly that there are many simulation tools these days from where one can predict whether at all, given the experimental parameters, whether pattern formation will take place or not over a certain angular window or not at all for the whole angular window, etc. Okay. Now, this is a very systematic study, and as I'm going to, so here this is the angle dependent study for silicon. Okay, the incidence angle was varied starting from 0 degree up to we went all the way up to 85 degree, but since 82.5 degree itself shows very flat surface, I'll show you why I claim that is flat, because so that's why I have avoided showing here another data of 85 degree or 87 degree till that angle of incidence, the sample remains flat. But in between, so many things happen, and beyond 51 degree, actually silicon surface starts showing up this ripple pattern formation. And you see very systematically how these ripples, that also I have not shown here because I have already shown the other day several times. From 65 degree onwards, I'm showing because these ripples, actually, the continuity starts breaking. A little bit of mount formation and broken ripples, etc. At 70 degree, it turns out to be mounts, and 72.5 degree, it becomes facet formation with a directionality parallel to the ion direction. The facets point towards that, and then needle-like structures pointing towards the ion beam direction. That's the next higher angle of incidence, and the similar trend or rather ripple orientation changes at even higher angle of incidence, 80 degree. Okay, and finally the surface becomes flat. How do you know that this flat surface? You look into the surface roughness that grows or varies with angle of incidence. So we started with the 0 degree angle of incidence. I have not shown here, of course. Any silicon surface, pristine silicon surface, will be having a surface roughness, commercially obtained wafer will have the surface in the order of picometer or the sub-nanometer. And you see here as well, surface roughness is almost definitely sub-nanometer as you go to these angles, 82.5 degree, etc. And sputtering yield also, you see, very important. Sputtering yield also comes down drastically close to nearly 0. as we reach this angle of incidence, that is in this case, okay, 82.5 degree or so, and it drastically reduces. And you can see that it's roughly fixed around 70 degree, 70 to 72.5 degree, which gets well manifested here. The ripple pattern is no more taking place at these higher fluences, at these fluences. And let me tell you, for this given set of experiments, this 5 into 10 to the power 17 ions per square centimeter fluence actually corresponds to an ion exposure time of 55 to 57 minutes. Okay. So what we see is sputtering yield curve is very similar to the surface roughness evolution plot. And so role of sputtering is immense. Okay, that's whatever people had assumed or tried to explain on many occasions that it can be nicely explained by Bradley-Harper theory was not wrong at all. Only problem is whichever report had shown or had reported that below 45 degree or below 50 degree no pattern formation took place, they are also they remain silent instead of trying to take a deal on it that why this is working against the prediction of Bradley-Harper theory. Nonetheless, we'll come slowly into that thing. And ripple rotation takes place through a series of different types of pattern formation for silicon for these given fluence. Remember. Now, this parametric phase diagram I termed and energy versus angle of incidence plot I had shown. This is the same plot, nothing new. All I want to tell you is in the linear regime, beyond 51 degree incident angle for 500 electron volt of argon ions on silicon, beyond 51, below 51 degree, the surface remains stable. That means no pattern formation was observed. From 51 to 75 degree odd, we could see parallel mode ripples in the linear regime. That means when the fluence was very relatively smaller. And because what I didn't tell you here is we did not restrict ourselves to only a fixed fluence. We started from very early stage of ion exposure time. So 2 orders of magnitude, 1 into 10 to the 15 ions per square centimeter, factually few seconds of ion exposure time. You can easily understand from 2 orders of magnitude. If this turns out to be roughly 1 hour, 2 orders of magnitude smaller will be roughly a few seconds to 1 minute, 2 minutes, etc. Very delicate that regime, small range, but we have very sophisticated equipment. And what we see here is the nonlinear regime. So all these patterns that we are reporting a day, these are all in the nonlinear regime. And those could be very important and exotic in terms of, or unusual in terms of various applications, possible applications. Okay. Now another interesting story here. You see the same ion fluence at 60 degree angle of incidence and beyond, for same ion fluence and beyond. Means what I say is ion fluence is varying, as I told you. This is 114 minutes. That corresponds to the 2 times higher fluence than this. Okay, roughly 1 into 10 to the power 18 ions per square centimeter was the ion fluence, and you can scale it down all the way up to here. So this is also for the same kind of order of magnitude of ion fluence, nearly similar, but 60 degree angle of incidence, not a big deal. 60 degree also, we should expect to see ripple formation. But why it has not taken place? All the way we are seeing everywhere this dot formation and mount formation, because this was the geometry we have discussed about. Okay, the ions are falling like this. If we consider this is the surface normal, the line drawn vertically, with respect to that we have seen several times. Okay, so this is the geometry. Okay, now if this is the angle of incidence theta, under this condition, you see that means the sample has been tilted already with respect to the incident ion beam. Now, under this condition, if we continuously keep rotating the sample, that is the azimuthal rotation is applied, then this kind of situation arises. No matter in the early stage, we get to see the ripple formation. Okay, but immediately, within no time almost, you get to see the end result. Okay, for a very early stage, for 1 minute, 2 minutes time, you still get to see the ripples. But as soon as you keep rotating it, for longer time, this thing turns into mount formation or dot formation. Now, what was our interest? Our interest was if we could go down in terms of reducing this dot size of silicon, it could be rather interesting. Rather, our intention was whether we could push it down, all the way near the quantum confinement regime. That means the dot dimension, had we been able to push down all the way up to 10 to 12 nanometer, we could see amazing thing in terms of light emission from these silicon quantum dots. Because as we know, silicon, away from this quantum confinement regime, is a very poor light emitter because it's an indirect bandgap semiconducting material. In contrast, it does become a direct bandgap kind of material, provided it reaches the quantum confinement regime, when the quantum confined atoms get into picture, and that happens depending on its size. Forget about silicon. For any material, that's very much in commonplace. So that's the important thing. But unfortunately, we could come very closely, but in spite of our tremendous attempt, we could not push the limit below 15 to 16 nanometer, if not around 17, 18 nanometer. So we fell short. So you can imagine how beautiful these silicon dots look like. Okay, but this is just to thrust that this is also kind of this matches with the prediction of Bradley's theory, and certain additional terms were actually introduced, and this resulted this flat surface science paper by us in collaboration with famous Richard Mark Bradley. Okay, and it was very kind of him to collaborate with us, but this was really fascinating results nonetheless. Here is an example of mostly putting one example just to compare. These are examples of what one sees in terms of germanium pattern formation. Okay, not so important, but just to share with you. Now look into this case where for a while, once again, I'll show you that what happens when this pattern formation takes place on the silicon or germanium or other material like SiO2 by using tens of keV energy. Okay, so you see ripples actually get coarsened that we saw yesterday through that linearly increasing wavelength with energy. So this is nothing new. For germanium also is very mature coarsened ripples were observed by us. And so this work is still in progress. I mean, analysis is going on, but nearly for the same influence, even for SiO2 at a lower angle, you can see beautiful ripple patterns, very mature ripple patterns actually evolve. Okay, so wavelength coarsening does take place and transition to sawtooth-like structures. That means this facet formation did take place for germanium. So similar features actually for below sub keV to tens of keV energy. This is an important observation, because when the community grows, when the community knows to understand for the sake of possible application-oriented research or to take it up to the industrial product level, one needs to know that again whether we can predict such pattern formation or not. And second aspect is how beautiful these patterns get evolved, such that depending on the dimension of the patterns, one can decide that what kind of application one can think of. So that's why I'm sharing this slide with you. Okay, and microstructure also plays a very important role. Okay, just I'll take a very small break for a few seconds. Let me drink some water. I'm there. Good. So here is the microstructure. As I told, microstructure is evolution is very important. This is a cross-sectional transmission electron microscopic image. obtained from a silicon surface which was bombarded by 60 keV argon ions at an angle of incidence of 60 degrees with respect to the surface normal. Here the geometry is shown very nicely. And we can see three clear zones which are getting created. One is the top layer which got amorphous completely. This white contrast says that it is an amorphous layer. We had confirmed it using selective area electron diffraction pattern. Okay, it showed the signature of this thing. In near these peaks, you can see these white circular objects here. Okay, as if nicely decorated. These two is the amorphous to crystalline interface, which basically arises at the end of the ion range. Any energetic ions, ion, when it traverses through a material, it is due to penetrate up to a certain distance from the surface of the material, and that's the well-known projected range of the ions. It depends on the ion energy, species, and the particular target material. Of course, it is also dependent on the angle of incidence. For instance, because of this cos theta term, this simple trigonometric calculation will show you that when the ion incidence angle becomes, instead of 0 degree normally incident, from normally incident ions to 60 degrees as we go, I mean, a factor of half comes into as a multiplication factor, and that straight away reduces the projected range by an amount of 2, by a factor of 2. It becomes half. So nonetheless, projected range is like that. And you can see another example or another way to illustrate you that whatever has been predicted earlier, that for curvature dependent sputtering, the valley regions get more eroded compared to the hilly regions. You see direct visual observation here or through this microgram. You see here the ripple. You see this thickness here is much less than this place near the hill. Okay, so at the valley it is actually reducing compared to the hill. Okay, so this is because the same energy, same material, but because of the fact that the valley regions get eroded faster compared to the hilly regions, okay, or hilltops, that's why we get to see this non-uniformity in the layer, this ripple layer. Okay, but nothing surprising. This can be explained like that, as I told you. Now, a magnified view of this region, these white bubble-like structures can be very easily solved when we look into a high-resolution TEM image, which very nicely show that these are nothing but bubbles. And through TEM EDX studies, that means energy responsive X-ray analysis studies during the transmission electron microscopic measurements, it got confirmed that these bubbles are made of argon bubbles, because we bombarded with argon ions at a very high fluence of 3 × 10 to the power 18 ions per square centimeter. So they get decorated near the hills. It's a complex process, and the amorphous nature of the layers were further confirmed from micro-Raman spectroscopic measurements. So apart from the pristine one, everywhere we see that signature of amorphous silicon broad peak gets created. And so higher thickness of amorphous layer arises in the front slope. Okay, that's because of the fact that I have already told you. Now, after a lot of simulation studies, we could show very clearly that both ion sputtering and this atomic redistribution contributes synergetically to explain our results. Okay, similar was the situation for germanium. We saw by 100 kV, 60 kV argon implantation ion exposure rather did not give much prominent pattern formation, although it was seen, but not so prominent like 100 kV krypton ion bombardment. And this is the very nice pattern formation took place. Here also through similar kind of simulation studies, we could match our experimentally observed results. Actually, argon ions are not supposed to show good pattern formation through these simulation studies. Okay, where both, once again, the erosive sputter erosive component as well as atomic redistribution combinedly contribute to the observed pattern formation. Here also these argon bubbles are formed, and here also in the front slope the thickness is more compared to the rear slope, because of the same reason that the valley regions get much more eroded compared to the hilly tops. And here also this layer is amorphous. Yet, as I was telling you, for silicon I didn't show it there, but you see very nice amorphous signature of amorphous rings present here, and from taken from obtained from the SAT patterns from this region, this amorphous region. Okay, and you can see, you can directly measure from the transmission electron microscopic image that the ripple wavelength is typically around 700 nanometer or so. Remember, on the other end, when you talk about 500 dB argon ion or krypton ion, there the wavelength is limited to some silicon and germanium to mere 30-40 nanometer. Okay, so higher energies, as we saw yesterday, this is the direct impact we get to see here. Okay, and we see the presence of krypton ions from these stem head of energy filter T images. Okay, and formation of a thin layer with bubbles is seen. So this leads to a change in density, etc., etc. For other property measurements, I will show you how it matters for hydrophobicity, nature of hydrophobicity, etc. from these surfaces. Now, this is a standalone example I'm showing you here to have exotic but highly ordered pattern formation in case of germanium at higher temperatures. These things, as I told you, up to 200 degrees centigrade, forget about 200 degrees centigrade for silicon. But germanium, up to 250 degrees centigrade, the surface remained flat. The surface remained flat. But you see the same argon ions, which otherwise do not give rise to any pattern formation on germanium surface at room temperature or up to 250 degrees centigrade, gives rise to tremendously different pattern formation. And so different surface instability actually works at higher temperatures, which is known as reverse epitaxy. So here, ion-induced amorphosity takes place beyond a certain fluence upon the order of 10 to the power 15 ions per square centimeter. However, due to the elevated temperature which is applied during this ion exposure, epitaxy, ion beam induced epitaxial regrowth takes place. But in this case, it is known as reverse epitaxy, because you see here we get to see through this checkerboard pattern, we get to see these are all inverted pyramids. So that's what it is. It grows from the bottom. So that's why it is known as reverse epitaxy. Okay. This was reported in Physical Review Letters a few years ago by one of my collaborators. Incidentally, it is the same group which had reported in Science in the year 1999 for the first time that gallium antimonide did show pattern formation that in the beginning that I showed yesterday as well as today. Okay, now this is, so for the pattern formation at elevated temperature is concerned, okay, important thing is, you see, fascinating ordering is possible to be created within the patterns. You see, at elevated temperatures for other semiconducting systems as well. You see, what is most fascinating here is nothing has to be calculated, nothing has to be tested. The ripples, the patterns are extremely highly ordered, is very much visibly clear. Okay, everything is visibly clear. So this is the example of 400 degrees centigrade, 300 degrees centigrade elevated temperature where pattern formation took place for 500 dB argon ions for all the 4 different semiconductors. Okay, and compound as well as elemental for germanium, and 410 degrees centigrade for gallium arsenide. Beautiful, absolutely grating-like structures are visible in nano gratings. And so is for gallium, for indium phosphide, gallium antimonide, and germanium. Now, these can be very nicely explained, as I told you other day, by invoking early soluble barrier, okay, which is dependent on crystal symmetry, and let us not get into detail. But important thing is, this kind of highly ordered pattern formation is possible in semiconducting materials by ion exposure, low energy ion exposure, for instance, and is possible when we put the sample or bring the sample at an elevated temperature. This temperature is not unique for any material. There could be correlation, just coincidence that here 300 degrees centigrade for indium phosphide and gallium arsenide give rise to some beautifully ordered patterns. Doesn't make much of a meaning. Same 300 degrees centigrade gives very different pattern for germanium and for gallium arsenide also. Okay, but to highlight this aspect, these are much more important and interesting for device industry, which is slowly coming up, because they don't like any randomness anywhere. Okay, although those are not bad patterns or badly patterned substrates to be used for other applications, but semiconductor device people which deal with these strategically important material like 3,5 materials like gallium arsenide or INP, indium phosphide or gallium arsenide. We all know these are IR sensitive materials with low band gap and direct band gap materials. So for defense applications and space applications, are very important. And here, if such grating patterns can be patterns can be generated, a lot of implications are going to be there. Apart from that, if I ask this question, is it the only way to do ion patterning at elevated temperature that one can observe such beautifully ordered patterns? The answer is no. There is another possible way out. Look into the germanium case. We may still use higher ion energy. Look, here the ion energy was limited to 500 electron volt to 1 keV or 2 keV or like that. We have done series of experiments, but here I have shown only 500 eV argon ions. But here you see the usage of 25 to 30 kV gold ions, although this example is for 26 kV gold ion precisely. Gold ions can also give rise to such wonderfully patterned germanium surface. What pattern? What an order! Fantastic. Now we have done a series of experiments and we have published a lot of papers in this regime. Here, important thing is that the implanted gold atoms actually can play a very important role, and this plays as a second component to give rise to highly ordered patterns, which is mandatory to change. Actually, this happens because of change in the composition of the near surface region of this material here, due to the implantation of gold and its and the very fact that it becomes a resident atom in the near surface region, which we'll show through different examples. Now, this happens at a very low, relatively lower fluence compared to those low energy ions, 5 into 10 to the power 17 ions per square centimeter. You get to see here that the ripples are broken. Not so much ordering at all. Double the fluence, ripples rather start going up, quite significant ordering. And I tell you, at 3 into 10 to the power 18 ions per square centimeter, the ripples are even much more ordered. Okay, of course, the ripple wavelength coarsening also takes place here as well. There is no reason why it will not take place. But see the difference, just double the ion fluence, we get to see this kind of fascinating ordering. And you see, these let's go back to this thing, cone-like structures, these facet-like protruding structures we get to see very easily. Something is very rough, goes beyond saying. This gives even ample indication that there are some granular kind of things. When you take help of cross-sectional transmission electron microscopic measurement, we get to see that flower-like structures actually are seen at the top of these ridges. Okay, so these are the pattern ridges. Okay, these white objects, they're sitting. These are the flower-like objects that we get to see very nicely, very periodically located. And through high resolution TEM imaging, we could observe the presence of germanium nanoparticles, the signature of gold nanoparticles, as well as a mixed phase of gold and germanium. All three are available within these amorphous layer, roughly around 10 nanometer, 10 to 15 nanometer thick, at the top of this crystalline germanium surface, which matches well with the projected range of the incident ions. Projected range means, as I told earlier also, the ions will come and stop, are due to stop here only. Gold ions of 25 kV or 26 kV cannot penetrate more deeper than this. And this becomes amorphous at this fluence expected. within this amorphous layer, including these flower-like objects at the top of the patterns, all these three kind of different nanoparticles are observed to be present. So how this happens is due to the ion impact through ion mixing process, gold and germanium actually combine together and forms a mixed phase of gold germanite. And then subsequently, over the cumulative process of long ion fluence, which was allowed to fall on the target, due to that phase separation also took place. So we got to see the presence of all three different kind of species. Like first the gold germanite forms, then it got space separated, means it broke into both gold individual components like gold and germanium. So in turn, what we expected is the implanted gold atoms may act as the second component to give rise to highly ordered patterns, is because of that fact. And that helps to alter the near surface composition, which is another key factor in this higher energetic regime to observe such wonderful ordered patterns. So ordered patterns, in summary, can be formed in two ways. Either we do the experiments with lower energy ions but at elevated temperatures, or else we can use a different ion rather than the inert gas ions. Remember, all these reports till now I have discussed, they were all formed by inert gas ions, just to make sure that the composition was not getting changed due to the incident ions, but here it is intentional. For higher energetic ions, much higher than 500 electron volt or 1 kilo electron volt, if we intend to create such highly ordered patterns, it is mandatory to alter the near surface composition, and that can be done only through by the choice of the incident ion, and rather a heavy ion which can give rise to the phase formation, and subsequently phase separation does take place. That is in nobody's control. Okay, so the change in the near surface composition is an important factor to create such fascinating patterns. These are some work function measurements. We get to see that work function also become anisotropic, like the morphology. Okay, along one direction you can see along one direction is the line profile of work function. So in the valley regions, okay, like in between these regions here, in between these two strips, the grating like structures, so nanowire like grating or grating like nanowire like gratings, if we call it, or nanowire like structures, in between the two nanowires, this groove region, when we talk about, their work function is quite less compared to the top or the ridges. Okay, and it is amply clear that they neither match with the pure gold work function or that of the known work function value of the tape used, or the pure germanium work function. So that's why, because we know by now through different other composition analysis related studies that gold germanite phase also exists. So that's why it is intermediate. Now I get into very quickly another 25-30 minutes time. I share with you very quickly the series of exciting results that we have reported, and few other colleagues from some other groups have also reported. And this will be now extended over those various research areas I had identified and that shared with you in the beginning. This will touch upon all those things. Let's start with the application of patterned silicon surface in the form of rippled silicon created at an energy of 500 electron volt argon ions at an incidence angle of 65 degrees. And that gives rise to these ripple patterns. And after that, subsequently, this group, again, this is the same German group that which reported in Science and Nature that physical review letters. This colleague of ours from India actually was a PhD student earlier, who is presently a faculty member in Ahmedabad. During his PhD work, he had shown that first you create such ripple patterns, and then at a certain angle, you grow silver nanoparticles on these ripple patterns. Okay, and simultaneously they had also took flat silicon substrate, a pristine silicon surface on which these ripple patterns were created. So before creating these ripple patterns, they separated out some silicon, pristine silicon piece cut from the same wafer, and they simultaneously deposited silver nanoparticles both on this flat silicon, that is a pristine silicon, and on this rippled silicon. And so nice on deposition takes place. The ACM image is so very categorically how the morphology becomes different. Basically, on the rippled surface, the silver nanoparticles grow in a conformal way, following the having a memory of this underlying substrate, silicon surface, where the ripples are formed. And here it also memorizes the morphology of the pristine silicon surface, that is usually a flat silicon surface. And after annealing at 300 degrees centigrade, these become almost pearl-like chain with pearls. Okay, so beautiful patterns. What they did is they used this surface morphological anisotropy to create plasmonic anisotropy for this sample, this metal frame. Okay, where they deposited the silver nanoparticles on the rippled silicon surface, the same rippled silicon surface. Okay, so what is seen here is along the ripples, they could show that along the ripples and across the ripples, like we are shown here. Okay, along the ripple and across the ripple, there was difference in the work function value. Like that, the reflection, optical reflection was also quite different along the ripples and across the ripple. Okay, that means along the wave vector and perpendicular to the wave vector of the ripple patterns. Okay, and of course, it was nearly isotropic. That means very nominal change for the similar studies performed on silver nanoparticle decorated pristine silicon surface, and a very clear signature of plasmonic shift. Okay, and this was nearly 0.2 electron volt. They have published a series of papers. We took a thread, and in collaboration with Dr. Ranjan, last year we have published this paper. We did, of course, very elaborate studies in terms of varying the growth angle as well. They had chosen one fixed growth angle, but they had, of course, varied the dimension of the silver nanoparticles, etc. But what we have done is we have chosen first to create argon-induced ripple patterns at an angle of incidence of 65 degree, and then we chose growth angle of 65 degree, 60 degree, 65 degree, up to 80 degree. Although I'll be limiting here data for few select angles, but we have done series of variation in growth angles for gold nanoparticle decoration. And you can see here also roughly the growth is conformal for higher growth angles, although the particle size is also quite limited. Okay, it resembles more like the case it happens here. The advantage of gold over silver is gold doesn't get oxidized so easily at all. Silver shows some tendency though. Okay, so to avoid that thing and to understand the role of near surface oxidation, etc., we had chosen gold. And we can see for all the growth angles, it is very nice to see that the plasmonic shift is optimal. Sorry, is highest for an optimal growth angle of 70 degree. This growth angle has nothing to do with 65 degree ion incident angle. This is gold nanoparticles were grown on this pattern silicon surface, as I have shown schematically. After this pattern surface is created, over that to decorate the pattern surface, the gold was deposited using e-beam evaporation in ultra high vacuum, basically an MB setup available with us. And what we got to see is that growth angle of gold, the gold flux arriving at the this rippled surface was from different angles. That angle was varied from 60 to 80 or like that. And so for 70 degree growth angle, we could see in contrast to the silver, where they had reported around 0.2 electron volt, we could see up to 0.37, nearly double. Okay, and a plasmonic shift of 107 nanometer was very clearly observed, while they observed only up to 35 nanometer for silver. Okay, so this plasmonic shift is also significantly higher for gold deposited on silicon, depending on the growth angle. So these are very important observations, because we have started some collaboration through Dr. Ranjan actually with the Tata Memorial Cancer Hospital for drug delivery in the cancer patients and so on. Because these gold or silver nanoparticles, they are very friendly for human bodies and blood and all these things. So significantly, reactivity-wise, one has not to think much. Okay, but drug delivery can be very important for cancer patients. So these kind of things where outside monitoring can be done through this plasmonic shifter now. Okay. Although I'm not an expert, but it's fairly interesting to get into such a collaboration slowly. Well, this is another example where we had done some studies where we had deposited aluminum doped zinc oxide, which is very well-known transparent conducting oxide for solar cell based research. And we could see up to a certain thickness here also the conformal growth took place. After that, this anisotropic morphology thing got disappeared and everything became same. When you see in contrast, the same film was simultaneously deposited on a pristine silicon surface. And here you see, this is the repeat silicon surface. On that, nearly 16 nanometer. Our nominal thickness was 15, but actually it was 15.9. Sometimes, depending on the ripples, actually. Otherwise, it was 15 to 15, 14, 15 to 16 nanometer of thickness. You can see here. So this is the aluminum doped zinc oxide layer. Okay. And we saw that anisotropy prevailed. That means a conformal growth took place. And what we did is we studied the photoilluminations from these samples, and we saw a clear blue shape up to a thickness of 10 nanometer or so. Okay, and this blue shape in the excitonic peak was seen up to 15 nanometer. And confinement movement effect can be a possibility for the observed set, but remember, this is not silicon. This is aluminum doped zinc oxide. This is a possibility. I mean, now I am going to share with you mostly the possibilities, what one can do by with the help of these pattern substrates. Now, I showed you earlier that at 72.5 degree angle of incidence, with the help of 500 electron volt argon ions when bombarding on silicon surface, the ripple patterns actually undergo a transition to, I told you, in the linear regime, it was still ripples. But in the non-linear regime, that means at a much higher frequency, you can see it straight away, 20 times higher frequency. Okay, so it's there. What happens is, or here 5 times higher frequency, it's in the non-linear regime. And I told you, and we stress again, these patterns created in the non-linear regime are actually very fascinating or interesting in terms of application. These patterns created, ripple patterns created in the linear regime always are not so interesting in terms of application, because the wavelength and the amplitude both are not so high. But here you can see roughness is very high. You can play it up. Conformally, you can grow many things on this. And this happens because of shadowing effect. I'm not getting into the details of these things. Now you see these facets once created. This is a glimpse of how they look like through a TEM micrographic image as a cross-sectional transmitter electron microscopic image, and you can see that the facets are crystalline. However, at the top or in and around these facet apexes, beat of signature name amorphous layer is seen, which could be a combination of native oxide formation as well as the amorphosity that the ions lead to. It's very, very difficult, even by transmission electron microscopic studies, to separate out the presence of these native oxide like SiO-related bonds and amorphous silicon. It's very difficult because it's a sub-nanometer kind of situation. But X-ray photoelectron spectroscopic analysis actually revealed the presence of SiO2, the presence of SiO2, basically the Si-related bonds, SiOH-related bonds beside the elemental silicon. And here also we did the photoemission study, and we see the blue emission. Okay, but this was mostly nothing to do with the silicon, but mostly because of the presence of these SiO-related bonds. Nonetheless, such faceted silicon surfaces can give rise, importantly, to blue light emission. Okay, and this is another example where the facets were shown to be pretty useful for reducing light reflectance. This light absorption can be significant, as you can see, compared to pristine silicon, which is here at 550 nanometer. You can see how much drastically it goes down for facets created at higher planes. Facets created at even higher planes, for instance, these facets, okay, they offer even a higher absorption, light absorption. Okay, so this is another example. And then both these ripple patterns and faceted surfaces could be utilized to deposit another transparent conducting material in the form of zinc tin oxide. Okay, zinc tin oxide gives rise to similar kind of reduction in reflectance, so basically light absorption. This was and then regarding the aluminum to zinc oxide, by varying the thickness of these aluminum to zinc oxide layer grown on the rippled silicon or faceted silicon, we could show that thickness dependent photoresponsivity actually helps improving the fill factor and light absorption as well. Okay, you can see thickness dependent shift in the absorption reflectance minimum is very clear, and the optimal thickness was 60 nanometer. So 60 nanometer actually gave rise to 30 nanometer, and that gave rise to pretty much good and optimized kind of fill factor, as well as 60 is here, not 30. So fill factor was highest for this. Okay. Now I get into last two examples, but these facets are very nice for exhibiting field emission property or cold cathode electron emission properties. We know the famous field emitter is LAP6, that is the lanthanum hexaboride, which is used as the filament in transmission electron microscope or scanning electron microscope machine. Under certain applied voltage, they start emitting electrons. Those are the beam of electrons which are used to probe probe for TEM machine or SM machine, etc. Now, it's always very important to try with other potential candidates which can also show field emission property. Silicon is never ever known as good field emitter also because of the presence of immediate presence of native oxide. Rather the presence of the native oxide, which forms almost immediately as the silicon surface gets exposed to the ambient conditions, almost unavoidable. And similar effect was observed and reported by many a group for any silicon-based nanostructure, even silicon nanowire, etc. And let us not forget the surface to volume ratio becomes extremely high for the nanowires or say low dimensional silicon structures, even killing the possibility. So it never did so. But we could show that through the variation in these facet dimension, the smallest dimension that the facets were created for the lowest unexposure time produce actually very stable field emission. You can see here, and as low as below 1 volt per micrometer. Okay, it's a very important finding with reasonably high enhancement factor of nearly 8,535, and falls into the scheme of famous Pauli-Nordheim equation, quantum mechanical tunneling phenomenon. However, we could experimentally show, as well as with the help of the DFT simulation studies, that the turn-on field actually increases with the increasing size of silicon nanofacets, I have already told. And the curvature-dependent formation of native oxide also plays a very crucial role. That's why the bigger facets are much more covered with the native oxide, as is marked here with these dotted yellow lines around the facets, bigger facets, and these are the smaller facets. So these corresponds to this highest ion exposure time shown here in the frame C. Okay, this one, and this one, this means frame A, corresponds to these facets, corresponds to figure number F, TM image. And apart from that, crystallographic orientation dependent work function is all responsible. Okay, and all these facets are although crystalline, apart from few here and there patches of native oxide plus amorphous silicon, very rarely. Mostly they are crystalline, and these are examples of large number of different crystallographically oriented facets This is an example of a large number of different crystallographically oriented facets. So all different crystallographic orientation means different work function. And this we have substantiated by DFT simulation strengths. Okay, it's different for silicon 100, 111, and 001, etc., etc. Now, interestingly, the question came in our mind then. This was reported in these two papers, series of papers. It says applied materials interfaces and applied surface science. And this, since it was interesting to note down or conclude that the smaller facets actually produced or exhibited much better field emission performance, the next immediate question came in our mind, and my next student followed up with this, Dr. Saini, that if we can reduce the facet size a little bit more and simultaneously can decorate them with metallic nanoparticles, can the field emission performance be further improved? And the answer is yes. Once again, these facets, along with those ripples, when they were covered with different by gold nanoparticles grown at different growth angles, exactly at the same time, that means simultaneously, we had loaded these faceted samples also, these faceted samples as well. And essentially, this resulted in formation of gold nanoparticles at different growth angles on those rippled pattern substrates as well as these faceted substrates. Purpose was one set of samples, the rippled ones, the rippled substrates were decorated by gold nanoparticles, were used for plasmonic studies, and here we tested the performance in terms of improvement in field emission property, and it worked. You can see growth angle does have up in terms of coverage of the coverage of the gold nanoparticles on these facets, the dimensions, etc., their shape, very clear. For this growth angle of 70 degrees here as well, it's optimal growth. The facet apexes get decorated with larger dimensional gold nanoparticles. Although very clearly the gold nanoparticles, those are decorating the surface of these facets a little smaller compared to the growth angle of 65 degrees. However, it's just these different dimensions that they grow at 70 degree growth angle creates very different performance. Now, again, these silicon facets are crystalline in nature, and what we found is very less amount of oxidation or say presence of amorphosity here. Hardly not been there. Because importantly, I had told you earlier, sir, we confirmed from several theoretical papers and these things and some our simulation study also that formation of native oxide is also curvature dependent. That's why smaller is the dimension of these facets. The curvature dependent native oxide formation probability reduces the presence of native oxide here compared to the bigger facets when it starts becoming more wider, and that's the reason we cannot ever avoid the formation of a very uniform native oxide on a flat that is pristine silicon surface. That's the reason. It's curvature dependent. So smaller is the curvature, smaller is the facet depending on the curvature dependent formation of native oxide probability. Here, smaller facets actually do the much more havoc in terms of this field emission performance and the absence of native oxide. And see, these are gold nanoparticles grown on these surfaces, and clear enhancement in performance. That 8854 enhances nearly double, more than double in terms of the field emission enhancement factor. And for silicon and nanostructures, I mean, you can imagine reported values were a couple of, or if not 5-6 volt per micron. From there, earlier we reduced to 0.67, and this time with the gold decoration, gold decorated smaller silicon facets, we could pull down all the way below 0.4 volt per micrometer. That's the turn on field. You can see very clearly for the 70 degree there is a S3 per prime. Okay, it's so very less. 0.39 mole per micron. And everything has been detailed. The spill enhancement factor for this case was 24,157. 18,152 was before annealing. Oh, I'm sorry. After annealing, we could actually reduce it further to 0.27 volt per micron. Amazing. This is lowest ever reported till then. And Dr. Saini and we together published this paper very recently, a few months ago, in Journal of Materials Chemistry C. Okay, so very fascinating results and realization. And we supported by a lot of finite element method simulation, where we could directly show that impact of field enhancement actually for bigger dimensional particles decorating the similar dimension of facets give rise to such enhancement in performance. This is another example. Let us not get into this thing. And this pattern surfaces, when we deposit titanium dioxide kind of thin films, very nice anisotropic resistive switching property also gets manifested. Dr. Panda has talked a lot, I suppose, in the morning. Unfortunately, I missed your talk. Tomorrow I'll be there. But important thing is resistive switching has already been introduced to you by Professor Panda. And I'm just telling you that here also very nice anisotropic resistive switching properties and actually neuromorphic computing properties also were revealed by my student Dilruba through these view graphs and conductive FM measurements, current map. And this is another study where gold implantation was done, and very nice ripple formation took place in the TiO2 films. Okay, and here also gold kept on increasing with higher influence. Okay, and resistivity started getting down. Okay, understandable. In the near surface region, it was very high presence of gold at mixed species due to ion implantation. And here also we could show nicely very fascinating result in terms of resistive switching, anisotropic resistive switching, and neuromorphic computing behavior. I'm not getting into the details. Okay. And one last example in the last 4 or 5 minutes. I come back now to the exhibition of nice anisotropic magnetic property when we use those highly ordered, patterned G surfaces. Okay. And what happens is we had grown cobalt thin films at different growth angles and at for different thicknesses, and we varied the thickness of cobalt thin films as well as growth angles, etc., to see how the ferromagnetic properties actually got varied, and at the same time that we could see magnetic anisotropy as well. You see how fascinating these patterns are. And this is the pattern. Okay, wavelength was 350 nanometer, and this group dimension, width of this group was nearly 110 to 125 nanometer, depending on different substrates. And when you grow cobalt at a normally incident flux, the cobalt grows in this form, absolutely conformal, grows mostly, get decorated mostly around the ridges, and of course a little bit gets into these groups also, why not? But for obliquely deposited cobalt films at an angle of 30 degrees, 60 degrees, etc., okay, we get to see how these columnar structures keep up. Okay, ridges become thinner, very clear. Wavelength remains same, but the width of the ridges actually reduces categorically. No second thought. Okay? And we can see the how the relative magnetization for normally deposited, normal flux of cobalt during its growth on this pattern germanium substrate, and the applied field magnetic field applied once along the pattern direction and other time by rotating the sample by 90 degrees. That means effectively the magnetic field was applied perpendicularly to this pattern. How the magnetization, relative magnetization changed is become very evident here. actually what happened is magnetically it became a little harder as we increased the fluence, because coercive field values actually loop opening is much more at fluences used to create the patterns at a lower value. Okay, and as and when the ordering increases with the help of more ion fluence put on the germanium surface, it became evident that the cobalt films grown on those kind of highly ordered germanium substrate, they become magnetically more harder. This is how the coercive field changes with increasing ion fluence. That means magnetic hardening is obvious with for the same 60 nanometer thick cobalt film grown once in normal orientation and then oblique incidence. And here the growth angle dependence becomes very clear. This is normally incident, this is 30 degree, this 70 degree, and so on and so forth. More or less, you can see the difference in the magnetization plots also, relative magnetization. And again, one applied magnetic field was once parallel to the pattern okay, along this direction, and once perpendicular to the pattern direction, and likewise, so we got to see this. Good example of these surfaces were created at very high fluence for silicon or say germanium. They could be good hydrophobic surfaces. Okay? I'm not getting into detail, just to say as possibilities are galore. This was also the work done by one of my past PhD students, and this is for germanium. This is our latest work. I mean, it got accepted last week. So germanium patterns, ripple patterns, or created at high fluence, or the textured germanium surfaces created at even higher fluences, can give rise to fascinating reduction over a large bandwidth, large wavelength range. Okay, real broadband starting from 300 to 3000 nanometer. You can see how less the reflectance becomes. Okay, for the samples, I mean samples created, that means these samples, where the ion incidence angle to create the textured like patterned germanium substrate was 16 degree, corresponding to a fluence of 3 into 10 to the power 18 ions per square centimeter, and that too corresponding to an ion energy, krypton ion energy of 100 kiloelectron volts, a lot of energy. And this gives rise to almost black germanium like this thing. Extremely low reflectance, less than much orders of magnitude less than 1%. Okay, so these are very clear signature of these kind of applications. And now I'm happy that I could maintain the given time by Dr. Panda. So these are the conclusions once for all. For such pattern surfaces, low and medium energy ion radiation can be used to modify and pattern surfaces on the nanoscale. And periodic patterns can be used as templates for thin film deposition. Substrate induces morphology dependent properties. Mostly anisotropic physical properties are exhibited by those substrates when we use them as substrates to create nanofunctionalized layer by through the growth of different value added or functional nanomaterials or functional materials in the form of thin films or this thing. And this extends as of now in terms of optical properties, magnetic properties, plasmonic properties, resistive switching or neuromorphic computing, as well as hydrophobic property and so on and so forth. The restriction is not there. Probably one has to see what best one can do. After the end of these two long talks, I must collaborate with I must acknowledge my large number of collaborators, including my very dear PhD students and postdocs who are doing all very well, and some are still in the training process, and many collaborators, the real stalwarts from several international places. And last but not least, thank you very much for your real kind attention for the 1.5 long hours of my presentation. And that also for continuously nearly 2 days. Thank you very much. Thank you very much to Devasis ji as well. I'm open for questions.
Thank you, sir. Just I like to tell one thing, sir. I have not discussed resistive switching today. Today, just we have discussed about the different vacuum technologies and those things.
Okay, that's great. I have not missed much, so I can hear from an expert tomorrow. I'm sure tomorrow you are going
tomorrow, sir, also we will discuss about the film technology only.
Okay.
Mostly we will discuss maybe little bit about resistive switching on Saturday, sir.
Okay. Thank you.
Yeah,
probably we'll keep it more for the third phase, correct?
Second phase, sir. Second phase we will keep most resistive switching.
Okay.
In second page, whatever in 15 to 20, that time we will discuss mostly on resistive switching.
Okay.
Please, if you have any question, please ask to sir. Sir, we have very vast knowledge. Please. I have already said.
If there is no question, always the basis I find it very common, which I have borrowed from few of our very learned senior professors, that can go either or directions. Like either the speaker has reached in every aspect with every slide, every point, every view graph, every statement to everybody, or else I could not reach at all to anybody.
So first one is impossible.
I would like to think that I have reached with all good parts, just to satisfy my effort. I mean, the jokes apart, all of you, please feel free to reach me anytime you want. Okay. So no
Mr. Anandraj, can you please you can unmute yourself and you can ask sir directly. You can unmute yourself. Please unmute and you can ask sir.
Hello, sir. I'm Anandraj, working as assistant professor at Rajlakshmi Jain.
Anandraj, sir, can you please, your voice is not audible here.
Yeah, it's very, very feeble.
Is it audible, sir, now?
Yes, better now. Yes, please.
Yeah, sir, I have just seen one of the observation in your presentation in the magnetic material. You have just shown two different hysteresis patterns have been observed at theta is equal to 0 and theta 90. For magnetic materials. Can you just tell me the reasons, sir?
No, see, basically the idea was to apply the magnetic field along the pattern direction and perpendicular to the pattern direction. That was the intention. So we had no other choice, just rather than physically rotating the sample by 90.
So you are just physically rotating it by 90 degrees. Sir.
Yeah, we just physically rotated the sample by 90 degrees during the method.
Yeah. Okay, sir. So it doesn't have any physical meaning over there.
Yeah.
Because most of the research paper shows that when they go for horizontal magnetic field, it shows a very narrow, narrow hysteresis. So is there
yes. That actually gets more hardened, as I told. I mean, as you apply perpendicular to the pattern direction.
Okay. Thank you, sir.
You are welcome.
Just one thing, I have already shared the feedback link for the whole day. I have also shared, sir, for this session test question. Some of you are not able to complete a second session question answer. So I have also shared for this one for their reference. I just inform. If you have any other question, please ask to sir. Sir, I think there are no more questions, sir.
No, I'm sure. I mean, at the end of the day, people are feeling tired also.
Yes.
1.5 hour long talks without any break, I mean, is more challenging for the audience rather than the speaker. Speaker will be always charged up, but the audience is not that easy.
Yeah, sir. Anandraj sir wanted to say something.
Yes, sir.
Please.
Sir, it's a takeaway from your talk. So, if the ion beams are considered to be as a quantum mechanical waves, whether these waves pattern are the cause for the ripples which are being formed by your observations in various samples, it's a wonderful work over there. Is that the things, the wave patterns of the quantum mechanical wave observation of?
No, we don't correlate with that.
Okay, sir.
Yeah.
Okay, thank you, sir.
It's a classical picture of ion matter interaction in a brute force method. You know, it's two-body elastic scattering.
Okay, sir. Thank you, sir.
Okay. Yeah.
Okay. I think there are no more questions. So some of the participants looking for the PDF file of these talks or all the talks, we will try to find it. We will ask all the speakers and also some sponsor also. If possible, sir, can you please share some of the slides at least because you have a lot of results up there. In
I mean, if
PDF
anybody
format.
is interested in any particular thing, Devasis, I will always be free to give it in person, no problem.
Okay.
That or those persons can always write to me, no problem.
Okay, that's better. So all of you, please, you can find the sir email ID in the IOP website. So please get it, or we will share in later. So I'd like to thank Professor Som once again for finding his busy from his busy schedule and a lot of time. 1.5 hour talk is not a very easy job, and for that preparation also it takes a lot of time. So I'm very much thankful. With 3 days talk sir is giving. So I'm very much thankful to Dr. Professor Tapobrata Som sir, and I also am thankful to all the participants for their patience. So with this, I am closing this today's session. We will meet tomorrow at 10 o'clock on sir. Thank you all, sir. Thank you all, sir.
Okay, once again,
Thank you,
thanks
sir.
Devasis for your kind
Bye.
invitation.